Hi everyone. I want to take you through a short lesson about dilutions. Up to now we've been learning about molarity in chemistry and what molarity or molar concentration is. And now we're going to move to the next step where we think about taking a solution that has a particular molar concentration and diluting it, and how do we calculate the new concentration after we've done that. Let's go back just a moment and do a very quick review of molarity. So in this last section we've talked about molarity, and it's really a fancy term for molar concentration. So if we're thinking about a solution has a concentration, and we use this term molarity to represent that. So if we think about a solution, for example, the one we've got here on our page, these little yellow dots could represent the moles. If we could see moles, which of course we can't with the naked eye, but if we imagine for a moment that we could, we'd see these moles of our chemical species floating around in our solution. And then we have a certain volume of solvent here. And so this is our volume. Maybe it's 100 mils, for example. And so we have some moles in solvent, and we use this formula: concentration is equal to moles per liter, or our moles over our volume. So we see this formula in our textbook where N represents moles of solute, and our V represents the total volume. Sometimes concentration can also be represented with square brackets. So you'll see this often in the textbook as well as in the course. And square brackets, again, are just a convention for showing concentration. So if we show the concentration of a particular substance, we can put square brackets around its formula, and that means concentration. Now, a really simple way to think about concentration, if we don't want to memorize the formula C equals N over V, is just to think about what it means. So concentration is just moles per liter. So it's the moles of our solute per liter of solution. And so this is a really great formula to remember. C is equal to moles per liter, and also we can use the unit capital M to represent moles per liter. So whenever you see that capital M, that means moles per liter. Great. Thinking about this now and going to the next step, which is saying if I have a solution and I want to change its molarity, I can perform a dilution. Dilutions happen all the time in everyday life. They happen in chemistry, and a really great simple way to think about a dilution is to think about your cup of orange juice in the morning. If you don't like the really, really strong taste of a cup of orange juice when you pour it from the container, you can add some water to it. And when you add the water, it tastes a little bit less concentrated, as we would say, because that's exactly what it is. You've taken a solution of orange juice, and if we add some water, we've performed a dilution. And if you're like me, I've got some kids at home, some young kids, and whenever I give them really strong orange juice, they get pretty hyper. So I usually put a little bit of water in there. So what we've done when we perform a dilution is we've simply added some more solvent, or added another solution, so that we still have the same number of moles of our solute. So in this case, we've still got the same number of orange juice particles, but we've now got a bigger volume, and so they are less concentrated. And that's essentially what a dilution is. We are less concentrated. We are changing the concentration of a solution so that it's not as concentrated as it was in the beginning. Here's a nice visual of that. So imagine here we have a solution of iodide, and initially, before we perform the dilution, you can see that there are 0.005 moles represented by these little purple dots in our solution. Now, when we add some water or another solvent to this same solution, we now have a more dilute solution over here, we still have the same number of purple dots. The same number of iodide molecules are still present in the solution, but now there's a greater volume of solution, and so they are, if we look at the close-up, we can see that there are water molecules now taking up more space, and so we see fewer of them in the same given volume. So over here, this was more concentrated. We see that there's 1, 2, 3, 4 iodide molecules in a given volume, and over here, once we've added more solute and they've spread out in the solution, we have fewer of them. So same number of moles, larger volume, which means that we go from a 0.05 molar solution to a 0.01 molar solution. And we use a really simple formula to calculate the new concentration, or perhaps the volume. There's a variety of ways we can use this formula right here, but this is the simple formula that we use. And it looks like this. If we start with an initial solution, okay, that has a specific concentration, which we call C1, and it has a specific volume that we call V1. Once we perform a dilution, we have a new solution that has a new concentration, and we call that C2. It also has a new volume, which in a dilution will be greater, and that volume is going to be V2. So this really simple formula, C1V1 equals C2V2, will allow us to calculate the new concentration if we're asked. It can allow us to calculate the total volume if we're given the other 3 variables. And we can rearrange it to calculate for any one of these 4 variables here. Let's do a couple of calculations together so we can use this formula and see how it's going to work for us. And most commonly, we're being asked to find the new concentration. Here's our first example. If we have 400 milliliters of a 0.800 molar hydrochloric acid solution, and it's added to 500 milliliters of water, what is the resulting concentration? Remember, these square brackets refer to concentration in the mixture. Sometimes it's nice to draw yourself a little bit of a picture if you're a visual person. So you can think to yourself, okay, I'm starting off with a 400 ml solution of hydrochloric acid. And that hydrochloric acid has a concentration of 0.800 molar, or moles per liter. I'm then going to dilute it by adding some water. Here's my bigger beaker. And I added 500 mils of water. So my total volume over here now is going to be 400 mils, which is what I started with, plus the 500 mils that I've just added. Great. There's our final volume. And the question is, what is the new concentration of hydrochloric acid? Okay, same number of moles are still present in this second beaker, but I've got a bigger volume, so my concentration has changed. Now we can go ahead and we can apply our formula C1V1 equals C2V2. And if you're a visual person and you've drawn your diagram, you can go ahead and label those right away. So I can see that C1 is going to be my original concentration of hydrochloric acid, and V1 is going to be my volume. Okay, and over here on the other side, my V2, my final volume, is going to be the new volume when I add the 400 mils to the 500 mils of water. And so what I'm really looking for here is the C2 in my question. If you're not a visual person and you don't like drawing diagrams, that's no problem. Another way you can organize the information in your question is to actually label it the way you see it in your question. So again, if we read it together, if 400 mils of 0.8 molar HCl, okay, there's our initial solution. So right away we could label that. There's our V1, there's our C1, is added to 500 mils of water. What is the resulting concentration? So we're looking for C2 right here. Okay, and our V2, we just need to be a little bit careful with in the question. It's not 500 mils. It's going to be 400 plus 500 mils, which is a total of 900 mils. But when you put it in your question like this, then you're ready to go. You can just plug it right into your formula. Let's go ahead and rearrange this formula. Remember, we're just solving for C2, so we don't want to have the formula written the way it is written here. We need to move this volume, V2, over to the other side. So we're going to divide both sides by V2 so that we have the following formula. C2 is equal to C1 V1 divided by V2. Now I'm ready to go ahead and plug the data into my question. And something sneaky is going to happen as we do this. Let's go ahead and start off. So C1 is equal to 0.800 moles per liter. Keep my units in my calculation. And I'm going to multiply that by V1. And notice something here. You can save yourself some trouble. You do not have to change your volumes to liters. Generally, when we're trying to find concentration in moles per liter, we always need to make sure our volume is in liters. But when you're doing a dilution calculation, because you have volume on the top and volume on the bottom of your calculation, you can have the units be the same because they're going to cancel. So it's fine for us to leave our volume in milliliters here because they're going to cancel out. So that saves us a little bit of time and a little bit of trouble. Okay, nothing wrong with converting these to liters. You're absolutely going to get the right answer, but you do not need to do that. So if we can save ourselves some work, why not? So 400 mils goes on the top. On the bottom, we added up our final volume, and it was 900 mils. And so we're going to go ahead and put that on the bottom, keeping our sig figs, keeping our units in our question. And right away we can cancel out of milliliters. Milliliters divided by milliliters is gone. And so I can go ahead and do the math. My answer is going to be in moles per liter because that's the only unit I have left that I have not canceled. And my answer is going to come out to be 0.356 moles per liter. Before I go ahead and report that answer, I should always check my sig figs. If we look back to the values that we used, we had 3 sig figs in our concentration C1. In our V1 volume, we had 1, 2, 3, 4 sig figs. Down at the bottom, when we added our 400 mils with 4 sig figs and 500 mils, we had 4 sig figs in our answer. 900.0. So our answer is limited to the least precise number, which was the C1 concentration. There was 3 sig figs there, so I'm allowed to have 3 sig figs in my answer. So it is correct. All right, let's do one final example here where we're going to use the exact same formula, but this time we're not looking for the final concentration. Here's our question. What volume of 8 molar, or 8 moles per liter, hydrogen peroxide, H2O2, is used in making up a 1.5 liter solution of 0.5 molar H2O2? Okay, sometimes you have to read that to yourself a couple times to think about what it's actually asking. Basically, we're starting off with a 8 molar, quite concentrated solution, and we are going to make a more diluted solution, and it's going to be a 0.5 molar solution that has a total volume of 1.5 liters. And so the question is, what volume of our original concentrated solution do we need to use? All right, so let's start by thinking about our formula. C1 V1 is equal to C2 V2. And again, we can go ahead and label right in our question what variables we have. So C1, original concentration, okay, of the more concentrated solution is going to be this one right here, 8 molar H2O2. There's my C1. In fact, this time I'll write it here, but I'll also write it off to the side for those of you who would prefer to set up your calculations this way. Okay, so concentration of our hydrogen peroxide initially is 8.00 moles per liter. Okay, what's the volume that we're using of that solution? Well, that's the thing we're trying to find out. What is the volume? That's the question. That's what we're solving for. Okay, once the dilution has been performed, we have a new concentration of our hydrogen peroxide. Those are square brackets, and it is equal to 0.5 molar. So there's my C2 right there. Okay, and our final volume we're told is 1.5 liters. So there's our V2. And we might like to just write that off to the side, keep it really nice and organized for ourselves, so that when we plug in our numbers we don't make a careless mistake. Okay, so I have my formula here, and I can see that what I'm solving for is V1, which is on the left hand side of my formula. So I need to isolate V1 by dividing both sides by C1. So when I divide both sides by C1, I rearrange my formula so that it is V1 is equal to C2V2 over C1, and I move that C1 down into the denominator. Now I have everything I need, and I'm ready to go ahead and plug in these values into my calculation. So C2 first, I've got 0.5 moles per liter multiplied by V2, which is 1.5 liters, divided by C1, which I know is 8 moles per liter. Keeping my units in my calculation. Great. So my moles per liter are going to cancel, and I'm left with liters as my unit of volume. And I can go ahead and calculate this out, and it's going to come out to be equal to 0.094. And my units, always using units in our answers, will be liters because we had our V2 volume in liters as well. Before I go ahead and finish this up, I should check all my sig figs and how many sig figs I'm allowed in this question. Coming back to my original data here that I see on the right hand side, I had 3 sig figs in my concentration C1. I had only 1 sig fig here for my concentration C2, and for my V2 I had 2 sig figs. So I'm actually limited in my answer to 1 sig fig, because this is a multiplication division question, and so my answer must be reported to have the same number or the least number of sig figs in my data. So I'm allowed to have 1 sig fig here. So that means I'm going to round it right there at the 9. The 4 is not quite big enough to round up my 9, so I'm going to leave it as 0.09 liters. And there's my final answer.